All right, now let's talk about Le Chatelier's principle. Le Chatelier's principle is a qualitative description of how equilibria change if a chemical reaction is altered in some way. And it states that if we change the conditions of an equilibrium system, of an equilibrium of a reaction that's at equilibrium, the reaction shifts and proceeds in a direction that will restore equilibrium, that will restore the equilibrium constant K. Okay, so you're always going to be striving to maintain K at the value, whatever value it's supposed to be at for a given reaction. So I'm going to present this as three cases. And the first case is if we add or remove species from a reaction. And I think, as with everything, the best way to illustrate this is by doing an example. So let's take a reaction where we have two sulfur dioxides reacting with oxygen to make two sulfur trioxides. So we have this equilibrium between both sides. Now let's write a K for this reaction. You should be able by now to write an expression for K for any reaction. And these are all gas phase species, so they're all appearing in the K. I have SO3 squared in the numerator and SO2 squared in the denominator multiplied by O2. So concentrations of all these things. Now remember, this is going to be a constant. K is an equilibrium constant. So this ratio is constant if we have a system at equilibrium. So now I want you to imagine what happens if we add more SO2 or O2, either of the reactants, to the reaction. Okay, so look at K. If we add additional SO2 or O2, we are making the denominator bigger, right? But we want to keep this ratio of products to reactants constant. So the reaction will automatically start pushing to create more products so that it can rebalance the reaction. If we add more O2 or SO2, the reaction will proceed further to the right, further forward to make more SO3 so that K can be maintained. I hope that makes sense. So if we add more SO2 or more O2, the reaction will shift to the right. So we could say shift forward, we could say shift to the right towards products to make more products. Okay, to the right, to make more products to reestablish K. So that is what Le Chatelier's principle is all about, predicting what the reaction is going to do if you make some kind of change. Now, you would get the same effect if you remove sulfur trioxide. So let's say I remove some of the sulfur trioxide as it's made. Now the reaction desperately wants to maintain K. So it'll shift to the right to make more sulfur trioxide. So I get the same effect by removing SO3 that I get by adding more SO2. Okay, so you get the same effect by removing SO3. So basically, by removing SO3, I create a hole on the right side of the reaction that needs to be filled. And the reaction will shift to the right towards products to fill that hole and maintain equilibrium. So conversely, if I add extra SO3, the reaction will shift to the left towards the reactants. And if I remove SO2, or if I remove O2, that creates a hole on the reactant side that needs to be filled. So removing either of those reactants will force the reaction to shift to the left to reestablish equilibrium. Okay. So Another way we can think about Le Chatelier's principle is by talking about what happens when we get changes in volume. And this only affects reactions that have gaseous species in them because we're talking about pressure volume changes. So you guys probably remember from studying gases that as we increase pressure, we decrease volume. So there's an inverse relationship between pressure and volume. So as we increase pressure and decrease volume, the reaction, if you have lower volume, the reaction will shift in the direction that reduces the overall number of moles of gas. To reduce the number of moles of gas. I'm going to show you some examples to illustrate this point in a second. So if you increase pressure, that is to say, reduce the volume, you have less room for your species to occupy. So the reaction automatically shifts in the direction to reduce the number of moles of gas. The opposite would be true too. If you reduce the pressure, you increase the volume, and that forces the reaction in the direction with more moles of gas, towards the direction that has more moles of gas. So in order to illustrate this, I want to give you 3 examples. So these are 3 example reactions. Let's look at the first example. H2 gas plus Cl2 gas combine to make 2 HCl gases. So what happens when we increase the pressure? Now remember, increasing the pressure is the same thing as saying we're reducing the volume. Decreasing the pressure is the same thing as saying we're increasing the volume. Okay, so you can talk about this in terms of pressure as well. Now, in the first case, you would have absolutely no effect on the equilibrium of the reaction by doing pressure or volume changes. And the reason is that, look, you have 2 total moles of gas on the left and 2 total moles of gas on the right. So if you have the same number of moles of gas on both sides, that means that there's going to be no effect on the equilibrium from pressure or volume changes. So same number of moles of gas on both sides of the reaction. In the second example, you have nitrogen reacting with 3 moles of hydrogen to make 2 moles of gaseous ammonia. So on the left side of the reaction, we have 1 plus 3 is 4 moles of gas total. And on the right side of the reaction, we have 2 moles of gas. So that means if we increase the pressure and reduce the volume, we're going to shift to the side with fewer moles of gas. And in this case, that's going to be to the right, towards the products. Conversely, if we decrease the pressure, we increase the volume and we shift to the side with more moles of gas. In this case, that would be towards the reactants. Now, in our final example, I have 1 mole of gas on the left and 2 moles of gas on the right. So if I increase the pressure and reduce the volume, I shift to the side with fewer moles of gas. And in this case, that's going to be towards the reactants, to the left, towards the reactants. Conversely, if I decrease the pressure, that will expand the volume. And that means I'm going to shift to the side with more moles of gas. And that, in this case, it's to the right, towards the products. Okay, so when you want to predict what's going to happen with pressure volume changes, you just need to count up the number of moles of gas on both the reactant and the product sides of the reaction. The final example of predicting what's going to happen using Le Chatelier's principle to equilibrium is looking at changes in temperature. And here you have to know something about the thermochemistry of your reactions, because the big hint here is that you kind of consider heat as part of the reaction. So higher temperature favors endothermic reactions, reactions that require heat input. So endothermic processes are going to be favored, pushed forward by higher temperatures. Lower temperatures are going to push forward, are going to favor exothermic processes. Okay. Let me do an example to put that kind of in the real world. Let's take a classic combustion example. Let's take the combustion of hydrogen. Okay, the combustion of hydrogen gas makes water. H2 plus 1/2 of an O2 molecule makes water. And we get a delta H for this of negative 286 kilojoules per mole of water. So this is an exothermic reaction. And in any exothermic reaction, heat is essentially a product because heat is released by the reaction. So heat is essentially a product. Another way of thinking about this reaction, we could even write it like this. We have H2 plus O2 reacting to make H2O plus heat. Heat is effectively a product in any exothermic reaction. For an endothermic reaction, we could write heat effectively as a reactant on the left side. So if I treat heat as a product, it's pretty obvious what the temperature effect is going to be. For an exothermic reaction, if temperature is increased, that's like saying that we have more heat, more product, and that's going to push the reaction to the left. So if temperature increases, an exothermic reaction like this shifts to the left to restore equilibrium towards the reactants. Okay, so since heat is a product, increasing the temperature adds more heat and it pushes the reaction to the left. We can also say the opposite. If temperature decreases, an exothermic reaction is going to shift to the right towards the products. And if it's an endothermic reaction, we would treat heat as a reactant. So for an endothermic reaction, if temperature increases, that reaction is going to shift towards the products, to the right towards the products.